All right, back once again. Here we are with the Chemistry 3202 review. This time we're going to look at Unit 3, Section 3, Lesson 4, this time on bond energy calculations. Now, bond energy calculations are going to be really easy because just about everything we're going to do here now, you've done something like it in one way, shape, or form. So let's go have a look at it. In this example, of course, it's dealt with on page 688 to 690 of your textbook, and there's a few questions there that you can give a try, and again, throw them at your online tutor and check it out. All right, this little diagram up here of bond energies, this is showing bonds that are happening between, say, carbons and hydrogens here, and this little ziggly line here is energy that's coming in and zinging, and the energy is hitting this bond here, and if this energy is sufficient, then this bond is, these two electrons are going to go their separate way, and we're going to separate this substance into two parts. If the energy is not sufficient, the energy comes in and it simply bounces off, and maybe this molecule gets excited. It may increase its temperature, energy, etc. But if the energy is sufficient, as it collides, it could be sufficient enough to cause the bond to break. Remember the collision theory, right? The energy has to be a sufficient intensity in order to break old bonds and form new ones. So that's what we're talking about in this particular lesson. We're going to say, well, how much energy does it take to break this bond and 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 this bond? All right, so we want to be able to say, well, if we know how much energy it takes to break this bond and how much energy it takes to break this bond and this bond, we should be able to add up all these energies, and that would be the total bond energy for this entire molecule if we wanted to pull it apart completely. So let's have a look at it. So here are the outcomes for this section. Define bond energy. Use average bond energy to estimate the delta H for a desired reaction. Now that's a very important little word there, estimate. We're only going to estimate delta H. More on that later. Keep that in mind, though. Okay, so what we're looking at here is the bond energy, and by definition, bond energy is said to be the energy needed or required to separate or break 1 mole of bonds between two different atoms. All right, so we're going to take a mole of a molecule, so 1 mole of water, and how much energy is it going to be required to break apart the bonds of 1 mole of water. So if we take something like hydrogen and say, all right, we want to pull apart these two hydrogen atoms because we want one hydrogen to go and react with something else, and this guy is going to go and react with another thing. So we want to pull these guys apart. And the answer is, well, it's not London dispersion, dipole-dipole, and hydrogen bonding and those type forces anymore, is it? It's the actual covalent bond now, and that's going to take a phenomenal amount of energy. It takes a significant amount of energy to break a covalent bond. So we want to separate these two joined, covalently bonded hydrogens to make two separate hydrogens that can go on and form new bonds with something else. And the value for this energy required to break the hydrogen-hydrogen covalent bond, it says it's a plus 486. So breaking bonds is a positive energy thing. Now we've seen this already when we talked about boiling water or melting ice. If we wanted to vaporize water, take liquid water and turn it into a gas, we had to pull apart the individual water molecules. We had to pull one water molecule away from its neighbor, and that we required pulling apart the hydrogen bonding, the dipole-dipole, and London dispersion. That's not what we're up to here. What we're up to is actually pulling apart a molecule, breaking that covalent bond, but nonetheless we have to break the bond, and therefore the energy required to do that is an endothermic thing. So all bond energies are positive, no matter if you're breaking a carbon-carbon bond or a carbon-hydrogen bond or any type of bond, a nitrogen-carbon bond, etc. All bond energies are positive. And the idea behind that is breaking bonds requires energy. So we're looking at this and we're saying, okay, if we can tabulate the amount of energy it takes to break specific bonds, then this is easy. You know, if we had methane, CH4, in order to break apart methane, we simply have to break apart 4 CH bonds. We look up our table for CH bonds and we multiply it by 4. Easy enough. Okay? So we would look these values up on the table on page 847. Now, one of the problems here with this table on page 847 is that now I got to tell you this one, all right? You got to watch out for the tables on page 847. Because on the table on page 847, there's bond energy tables, and there's also bond length data. Okay, so if you confuse bond length information with bond energy information, the tables look almost identical. Be very careful. You pick the one that says bond energy. All right, you'll see what I'm talking about if you flip open to page 847 of your textbook. All right, now these bond energies are considered to be average, and that's why you'll see on the top of the table it says it's a table of average bond energies. Now, what we mean by that is we're saying we're assuming that every single bond is identical in every single compound and every single substance, and that's not true. And I'll give you an example to show you what I'm talking about. Here we've got an example of 4 molecules, or 3 molecules here, 4 molecules actually. 3 of them have a hydrogen and an oxygen bond, right there. If we go to the table and say, how much energy does it take to break that carbon, that oxygen-hydrogen bond, the table really doesn't know what molecule it's coming from. All the table is all that information is saying is that the energy it takes to break an OH bond is this much. And it's not taking into account the other thing that the oxygen is being bonded to, is it? Because every one of these atoms, like this carbon, has an electronegativity of 2.5. Oxygen is 3.5. So is the pull from the carbon going to influence any pull here in this bond? Or are these bonds independent from one another? Like, does this bond have nothing at all to do with that one, even though it's bonded to the same oxygen? And is this bond here going to be the exact same energy as that one? You know, this oxygen's bonded to a hydrogen in this case. Here it's bonded to a carbon. So we'd have to think that, hey, maybe that carbon is influencing everything about the oxygen. And maybe that hydrogen doesn't have as much influence as this carbon because the hydrogen has an electronegativity of 2.1. So the table really doesn't take into account the influence of the other things that are in the bond. Okay? Likewise here, is the bond here going to be influenced by this? Well, absolutely. Because that hydrogen there is an acidic hydrogen, isn't it? That's pretty easy to come off. That bond right there breaks as soon as I put it in water. That OH is going to be pulled off. I put that in water, that OH stays where it is. This is not acidic. So we're saying that, yeah, what that oxygen is bonded to on the other side is going to matter. And in this case, it matters a lot because that hydrogen is really easy to come off in water, right, breaking that bond. So when we look at the table really doesn't distinguish what the OH is bonded to. It's just saying, okay, let's average all the different situations. So that table value you get is only going to be an average for all the different instances of where we might have an OH bond. Likewise, here we've got 3 hydrogen-carbon bonds, CH bonds. Here we've got 4. Are all 4 of these going to be the same as these 3? Probably not. Is that oxygen going to influence it? More than likely. Does it matter which one comes off first? Are all 4 of these going to break at the exact same time? Well, we looked at the collision theory and we said, that's unlikely. We usually like to have one thing happening at a time. When you have more than one thing happening, then that complicates matters. So the answer would be, well, if this is coming off one hydrogen at a time, when this first hydrogen is removed, are the other 3 going to be held a little more tightly or a little more loosely, right? Is it going to be easier to take off this hydrogen now that this one's gone? And as we start pulling them off, now are the other 2 going to be easier or harder? So you get the idea that it gets complicated. So in order to just make things a little easier, we say let's average all these bonds. And once we do that, we say, well, now our final answer that we're going to get here is not going to be as accurate as we might think it is, really. Like these values that we're going to calculate now are saying, well, these are averages. So we're in the ballpark, but it's not going to be dead on. The best way to find values, of course, is using the Hess's law that we did in the last example, right? That gives us excellent results, deadly results. But here, our values are only going to be averages. So we're assuming then, and this is the problem, anytime you make assumptions, isn't it? Just like calorimetry, remember we had those 4 assumptions? We're assuming everything was perfect, but we know it's not. Anytime you start making assumptions, that's when you start leading to discrepancies in your final answer, errors in your final answer. And as long as we're aware that there are going to be discrepancies, then okay, we can account for that in calorimetry. We know that we're not going to get a perfect answer, but we know we're going to be in a very good ballpark, and if we do everything carefully, then we should get some nice results. In this case, no matter what we do, our results are always going to have discrepancy because our values are based on averages. Okay? And there we go. So we're looking at this and we're saying this is a very important point down here, and this is worthy of a footnote, big Sasquatchy footnote. Here we go. Sasquatch's left foot. Okay, put his rubber stamp on that and saying this method at best is only going to be an estimate. All right, so it's only going to be an estimate of the actual heat of reaction here because the values we're using are averages and they're estimates. So there we go. So you might say, well, why are we doing this? Well, it can give us an idea of what the ballpark figure is going to be. And let me give you an example to show you what I'm talking about. Okay? Now, the bond energy formula, if we wanted to do this overall, remember we just said back here that if I wanted to figure out how much energy would it take to break this guy up entirely, let's count every single bond that's here. Well, our bond energy formula is going to do that for us. And it's very similar to the one that we just seen here with Hess's law, except I've got a little thing here. I'm going to say I've got estimate put here. Now, it's probably not correct to put estimate there, but that's just an idea for you guys to say, yeah, this value is an estimated value, and it's based on the sum of the bond energies of the reactants minus the sum of the bond energies of the products. Now, you notice anyone who's on their game here looking at this and saying, that's a mistake there, that's a mistake. Wasn't the last one products minus reactants? It absolutely was. In this case, it's reactants minus products. And I'll tell you why in a minute. All right, so we're going to shorten this up and we're going to say the estimated enthalpy is going to be the sum of the reactant bond energies minus the sum of the product bond energies. Okay, and we want to watch this equation because we don't want to confuse it with the heats of formation. All right. And the bond energy values that you're going to use are on table on page 847. And again, don't confuse with bond lengths. I know someone who's very dear and close to me who's doing chemistry, and they couldn't get any of these answers to work out. And I said, you're not using the bond length table, are you? Oh, yes, that's what I use. So every single question she done, she had to do again. All right, be very careful. They're side by side. You guys have to use the average bond energy. Okay. Here's the data table that you would get with your public exam, and I just wanted to bring this up because I made reference to it several times, and I'm looking at this and I'm saying, yeah, well, there's the equations right there. Look. They also give you the quadratic equation down here, right? Remember we did that with ice tables and acids and bases. They also give you a solubility table. All right, if you need to find out what's precipitated or not. They also give you complex ions over here. Right, if you need to write some chemical formulas and stuff. And they also give you a bunch of constants here, right? But what we're interested in, of course, are some of these formulas that we're going to be using, and there they are. So some people, I corrected the public exam a couple times now, and some people have difficulty even writing the right formula for some reason, and say, well, how come they got the formula wrong? You know they know the formula of pH, or you can't remember it. Well, there it is. All right, you know the heats of formation is products minus reactants for formation. That's an F there. And you know bond energies is reactants minus products. So there's no way you should mess up this equation, all right, because it's there. And if you mess up your quadratic equation on your acid-base calculation there, there's no excuse for that either, right? So if you mess that up, they don't give you a mark for trying because, hey, it's there, it's given to you. So keep that in mind. All right, so here we go. Here's a problem that we're going to look at. We say, okay, let's calculate the estimated enthalpy for this. So we're going to take some ethanol, C2H5OH, and we're going to react it with 3 oxygen to produce 2 carbon dioxide and 3 water vapor. Now, I just wrote the chemical formula up here, C2H6O. That's the chemical formula for ethanol. We're going to come back to that now in a second. But how do we go about doing these problems? Well, the very first thing you have to do is you have to consult your knowledge of Chemistry 2202. and be able to draw a Lewis dot diagram and then a structural diagram. And a couple things you have to keep in mind here if you're not sure about that. Carbon makes 4 bonds. Hydrogen makes 1 bond. Oxygen, even though it has 6 electrons in its outer shell, it only needs to make 2 because of the octet rule. So each carbon needs 4 bonds. It can be doubles, triples, or singles. Each oxygen needs to make 2 bonds. It could be a single or a double. And each hydrogen makes 1 bond. So what we have to do is actually draw the structure of an ethanol. And we're saying, okay, it's C2H5OH. And this is going to be very important, isn't it? Because the chemical formula really doesn't tell us how the carbons, hydrogens, and oxygens are arranged. This structural formula here, C2H5OH, is telling us that we've got an OH bond here. All right? So when we look at this, we're simply counting the numbers and types of bonds. I've got 5 CH bonds. I've got 1 carbon-carbon bond. A lot of people forget about the carbon-carbon bond when they do these questions. For some reason, they just take the things on the outside. But no, there's 1 carbon-carbon bond here. There's a CO bond, single bond, and there's an OH single bond. So what I'm going to do is I'm going to list all of these and get the values from these off the table, and I'm going to add them up. So what I'm doing, I'm saying 5 CH bonds from my table, 1 CC bond, 1 CO bond, and 1 OH bond. I get the values from the table, I multiply the number of bonds I have, and I add them up. Okay? So that's the amount of energy required to break every single bond in ethanol. I then look at oxygen, and I say, okay, what's oxygen going to look like? Well, oxygen, a lot of people think oxygen has single bond, but really oxygen is double bonded. And now you've been told, so don't forget it. All right? So in this case, oxygen has a double bond, but you got to watch here because in this case we only had 1 methanol. In this case we've got 3 oxygen. So we've got 3 of these that we have to break up. Okay, what have I got done here? Uh-oh. Hold on, give me a second here now. There we go. Everything's in order here now. Okay, so we've got 3 oxygen molecules that we have to break, 3 O2s. So what that means is I have to use the amount of energy to make 1 of these break. All right, I have to break the first one apart. I have to break the second one apart, and I have to break the third one apart. So in reality, what we have is 3 bond energies of O double bond O that we have to break. Now, what's O double bond O? Do we just go get O single, and add them together? No, absolutely not. A double bond has a different energy value than a single bond. So O single bond O has a different energy value than O double bond O. All right, so make sure you use the correct one. And you may have to search down through the table to find that. All right, so we find that value from the table, and of course there's 3 of them, so 3 times 498, and that equals 1494. Now, that's the amount of energy it takes to break 3 of these oxygens apart. Now what I'm saying is, that's now the energy of my reactants. Okay? What we do next is we proceed then to do the products. Carbon dioxide, once again, you do your Lewis dot diagram, you do your structural diagram. Carbon needs to make 4 bonds. Oxygen makes 2 bonds. So in this case, we're going to have double bonded CO, double bond CO. Now again, we have to watch this because we've got 2 of these guys that we are dealing with, not just 1 carbon dioxide, we're dealing with 2. And a lot of people make that mistake on the public exam, is that they'll do 1 for ethanol, then they'll only do 1 oxygen, and they'll do 1 carbon dioxide. But in actual fact, there's 2 of these guys, so you've got 4 C double bond O's to break. So I look up my chart, and lo and behold, 4 C double bond O. Now that's a different value than C single bond O. Over here, C single bond only takes 358 kilojoules to break. A C double bond O is going to be a slightly different value, and it's way more. It's 745. Okay, it's more than double, even though it's a double bond. All right. So we do our multiplication there, and it works out to be 2988. And then we look at water, and again we say, okay, we know what water is. Water is this single bonded compound like that, H2O, and we've got 3 of them. So in reality, we've got 6 OH bonds. I don't know how many people are going to give me 3 OH bonds. There's actually 2 for each molecule. So 6 OH bonds. And there we go. OH is 6 of these, so 6 times 460 is 2760. Now, you see the big difference here. Like, when this first hydrogen comes off, do you think this guy's going to come off any easier, or is it going to be harder? I mean, that's going to change the dynamic of that water molecule tremendously in order to pull off that hydrogen compared to this guy. And remember now, water is amphoteric, isn't it? So water is capable of donating hydrogen. That one comes off easy. But we're going to be left with OH, which is going to be held very tightly. So these 2 hydrogens are probably going to have different bond energies as opposed to this one over here. So we're assuming that they're the exact same bonds. And again, that's a big problem. Okay, I digress. What we have here now is the bond energies in order to break all the reactant bonds. We have the bond energies here in order to break all the product bonds. Now you might say, breaking products, sir. Aren't we really forming these? And the answer to that is, yeah, we're breaking the product. We're breaking the reactants. We're forming the products. So if these are all positive values, these guys over on the other side should end up being negative values. And you know what? That's why we have the equation as we do. This negative sign right here is saying, okay, I'm going to add up all the reactants, plus, 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 and then I'm going to take the negative of the products, and that's what the negative sign does. So I'm going to add all these guys up, plus, 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 and then I'm going to change the sign of them. And that's why we have reactants first, products second. Because every single one of these values are going to be positive, I need to take into the account that on this side, I'm breaking bonds, which is positive, and on this side, I'm forming bonds, which is negative. Breaking is positive, forming is negative. Okay, so here we go. We put our values in, and we simply sum these guys together, and then sum these and subtract them. There we go. And what we get is negative 1399 kilojoules. So what we're saying then is that there's more energy released as these bonds formed than there is when these bonds break. Does that make sense? Well, we're burning ethanol. It's a combustion reaction. We're burning it. People burn that in their cars. It's a combustion reaction. It's exothermic. So there's more energy released as the new bonds form than there was required to break the initial reactants. And that, where does this extra energy go? Well, it goes to the environment. Drives your car, heats up water. You see a flame, right? Energy is going to be lost. How much is lost? That much. Okay, let's try another problem. One more problem. This guy here now is acetone. And you notice here it's got the exact same chemical formula as the ethanol on the other side. Let's go back and look at it. C2H6O. This guy here is C2H6O. So we're saying we're burning ethanol. Let's go over on this side and say let's burn propane. It's the exact same chemical reaction. 3 oxygen, 2 carbon dioxide, 3 water. So would we expect to get the exact same delta H value? You might, but the big difference is how the acetone is put together. Oh, sorry, not the acetone, the dimethyl ether. Sorry about that. Ixnay on the acetone nay. It's diethyl ether. All right, so what we're looking at is how the diethyl ether is put together here. And we're saying, okay, same thing, count the number of bonds here. Don't forget we got a CO bond and a CO here, so there's 2 CO bonds and 6 CH bonds. All right, so we'll do the math on that real quick. 6 CH bonds, 2 CO bonds, da-da-da. Okay, we do the oxygen. Once again, we have to remember that we have 3 oxygens here. So 3 O double bond O. We do the math on that. Then we look at our products and we say, okay, again, 2 carbon dioxide, so that's 4 C double bond O's. I'm going quick here because it's the same thing. And then water is going to be 3 water molecules, which is meaning it's 6 OH bonds. So we do the quick math, look up the table on that. Okay, I got to clear that up there. Okay, let me just fix that. Holy cow, what am I doing? 6 OH bonds right there. Okay, there we go. So now we've got our reactants and our products, and again we do the same thing. And again, look, we're breaking bonds here. It's positive. We're forming bonds here, so that's what the negative sign refers to, and that's why it's in a different orientation. Okay, let me just make this a little bigger for you. Okay, we put our values in, and lo and behold, we get our math done, and we're saying, whoa, 1502, is there some kind of mistake here? So even though they're isomers, they've got the same chemical formula. The difference here is they've got different structures. They have different numbers and types of bonds. Let's go back and look at it. This guy has 6 CH bonds and 2 CO bonds. If we go back and look at the other one, there's 5 CH bonds here. There's 1 CC bond, there's a CO bond, and there's an OH bond. So by putting it together in a different structure, we're dealing with different numbers and types of bonds. And therefore, because of that, we end up seeing different values, even though it's the exact same combustion reaction. Okay? So there we go. So the question that would come up would be, you know, one is 1399, the other one's 1502. That's a difference of 103. Why then would it be a different value? Okay, that's the answer for down there, by the way. The answer to this guy here, we get 1399. We expect 1502. That would be for the first one, for the second one. And the answer would be, of course, that this is based on estimated values. And that's very important that you understand. That's what we talked about in the beginning. We don't expect to get exact accurate values because the numbers that we're dealing with are not exact accurate values. They're estimated average values, and because of that, we're going to get an estimated bond energy. Are we close? We're not bad. We're not real good, but we're in the ballpark, and that's the purpose of this, is to try and find out what the ballpark figure is. And in the last question down here, it says, what do you notice about the empirical formulas of ethanol and dimethyl ether? They're isomers. They are the same. They got C2H6, but because they got different numbers and types of bonds, they're going to have different values. All right, so that's how we account for the different bond energy. Okay, one last little summary here. We now know at the end of this, we finished enthalpy here now, and we now know 4 different ways to find an enthalpy change. So let's analyze the 4 ways, and we're saying, okay, the first way is through calorimetry. Experimental error, we've got assumptions. We're doing it based on our surroundings, so we could do something like this. We could say Q of the surroundings equals MC delta T, and then we're going to do Q of the system equals minus Q of the surroundings. And then we're going to get delta H by saying delta H is going to be Q over N. So this method involves measurements. Anytime you involve measurements, you can possibly get experimental error. Calorimetry itself is filled with assumptions. Remember those 4 assumptions of calorimetry. If you can't, go back. And therefore, this guy is going to be based on assumptions. So the accuracy here is going to be limited to how accurate your experiment can be, how accurate your equipment is, how pure your starting materials are, and the fact that it's based with assumptions is going to give you problems. The second way we said was Hess's law, the summation of equations. And we said we're going to get good results here, but it's going to be difficult to choose correct combinations. And because of that, it's going to be limited to what formulas and equations we give you. All right, you're not going to sit down on a test and try and figure out all these different equations that you might have to flip around and change over and backwards. And what if you pick one wrong equation? That could lead you down a path that you might have to use 20 different equations to get you back type thing. So pretty much a jigsaw puzzle there. So problematic, can be done. We'll give you the values. The other way, of course, formula method, heats of formation. These guys are based on heats of formation tables. They're accurate values. They're the accepted values that the scientific community would use to try and find heats of reaction. This would be the value that you would compare every other one of these measurements to. So this guy here is definitely the best way, the most accurate way to find your heat of reaction or your enthalpy. And finally, the fourth way, of course, was bond energy. And this guy, of course, is only approximate, so it's going to be an estimate. All right, so this would be the most accurate. This is the standards. All of this would be compared to this one. And let me fix that for you now. So that's the best one. The other three, of course, it depends on what you're doing. Number 4 is only an estimate anyway, so it's only going to give you a ballpark figure. Number 3, if I did a calorimetry experiment, in order for me to figure out how good my experiment was, I would get this value here, and I'd say, okay, let's do this and see how close I am to this value. There we go. All right, I'm going to stop there now. Make sure you take advantage of the online tutor, once again. And make sure you go get some public exam questions to see what types of questions they're going to ask you here. Sometimes long answer question, sometimes multiple choice, most times multiple choice, right? Because they could give you a real simple calculation here, and you'll have to calculate the bond energies. All right, I'm going to stop there now, and I'll see you next time. Bye-bye.